focus 2 is about energy and is the introduction really to the study of the modifications and changes that energy can undergo in the form of thermodynamics. So here is the introduction to the first law of thermodynamics. What you should bear in mind as you approach thermodynamics is that each of the laws introduces a crucially important property. The first law introduces energy. The zeroth law, which I'm not talking about, introduced temperature. And in due course we will come to the second law, which introduces entropy. So those three major properties of matter, temperature, energy, and entropy, are introduced by the zeroth, first, and second laws of thermodynamics. And this particular focus looks at the properties of energy and establishes the first law. Energy is introduced through the first law, and it's a particular aspect of energy, which is the internal energy. So we're not interested in the total energy of a sample that is flying around the Earth or moving around the solar system or moving through the galaxy. We're interested in what we find internal to our sample of energy, of our sample of matter, and that is the so-called internal energy. And the internal energy arises because people realize that there are two ways of changing its value when you have a system that you cannot penetrate with matter. So in a closed, so-called closed system, you can get through the walls by doing work. And work is a well-known and well-understood mechanical process. You can also get through the walls by, if there is a temperature difference, and the change of internal energy that takes place inside your closed container then depends upon the quantity of energy that has been transferred as heat. So, but once you have changed the state of the system, either by doing work on it or by transferring energy as heat as a result of a temperature difference, it no longer matters how you got it in there. Energy is energy, and you can use it. You can put energy in as heat and draw it out as work. You can put it in as work and draw it out as heat, and so on. So the internal energy behaves like a bank, where the currency that you use is either heat or work. Chemists, though, are interested in measuring changes under certain conditions. And one of the conditions that is most commonly applied in a laboratory is, of course, constant pressure. So many changes take place at constant pressure. But the trouble with that is that when a system is at constant pressure, its volume can change, and therefore it can do work on the atmosphere, on the surroundings, even though you're not interested in that. So what thermodynamicists did was to find a cunning way of modifying their perception of internal energy, which enables them to take into account these changes due to work seeping out automatically. And to do so, they introduced the concept of enthalpy. Now, the word enthalpy means heat inside, but you should never think of it like that because, once heat gets in, it's energy. And you shouldn't really think of something as having a certain amount of heat. It has a certain amount of energy. But the enthalpy is really introduced in the interests of bureaucracy. It's a way of doing calculations that takes into account automatically the fact that the energy you're putting in doesn't all stay inside. Some of it leaks out by doing work of expansion. And so what the first law does by introducing enthalpy is to find a way of talking about the system alone, which automatically takes into account the fact that energy is leaking out of it by doing work. Then you're not normally interested in that wasted work, but you are interested in the precision of bookkeeping, and enthalpy enables you to do that automatically. And of course, once you've got enthalpy under your belt, then you can apply it to one of the major regions of interest in thermodynamics, which is thermochemistry. And thermochemistry is all about the energy that you can extract or need to supply as heat in systems. So it applies, of course, to a discussion of fuels and food. But it's also, of course, a much wider relevance than that, because once you have got enthalpy underway, you've got really a hand on the changes that are taking place inside the system, and the enthalpy is used in other thermodynamic functions, which we'll come to in due course. Now, one way of making progress in thermodynamics is to focus attention away from large changes into infinitesimal changes. And I think this is probably the crucial step in thermodynamics that people don't realize is absolutely essential to what they're talking about, which is to focus on infinitesimal changes. Because if you have an infinitesimal change, you might be able to focus just on the infinitesimal change in, say, temperature, or infinitesimal change in volume, and forget the consequences that might arise if you made a measurable change in volume or temperature. So it really focuses you on the individual changes in the parameters that are under your control. And having done that, it also opens up the route to mathematical manipulations. It's really the interface between chemistry and thermochemistry and mathematics at this point, because you can bring all the power of the calculus to bear on the problems of thermodynamics once you focus on infinitesimal changes and use the properties of the infinitesimal calculus. So it's a crucial step in understanding. And although that might sound a bit frightening, it actually isn't, because the mathematics that comes into thermodynamics is really pretty trivial stuff, really. Or so it seems at my distance. So here, in this particular topic, we introduce the concept of the infinitesimal change and that overridingly important property of the internal energy and the enthalpy, which is that it is a state property. A state property is something that has a value that is independent of the way that you prepared the system. So you can prepare the system in a whole variety of ways, and provided it is in the same state, same temperature, pressure, volume, same amount of substance, then it will have the same internal energy and the same enthalpy. Crucially important aspect of thermodynamics, and one that you have to keep in mind. Then there is finally in this focus, there is a very special kind of process that is a bit boring to deal with, but actually turns out to be of great importance once you get down the line in applications of thermodynamics, which is the adiabatic change. An adiabatic change, as you can tell from its name, means one where something is not passing through the walls. Diabatic boundaries are transparent to energy as heat. Adiabatic boundaries are opaque to energy as heat. So although there might be a temperature difference between the system and its surroundings, energy does not pass through as heat. So an adiabatic change, although slightly tedious to deal with, is actually very important for the development of thermodynamics down the line, because in many cases you are dealing with systems where they are in a thermally isolated container and heat cannot pass through the walls. So in this particular focus we have introduced internal energy, a state function. We have seen that if you want to do calculations that automatically take into account the work that leaks into the surroundings when the system is at constant pressure, then you talk in terms of the enthalpy. And we have seen that by switching attention to infinitesimal changes, you're given great power, because you can bring the power of mathematics to bear on thermodynamic problems. And we've concluded with meeting a type of process, an adiabatic process, which will play a crucial role in later developments.